Hello everyone, I'm Mark Sutherland and I'm a PhD student here at the Parallel Systems Architecture Lab at EPFL, and I'm here to talk to you today about some of the cross-layer research that our lab does for tomorrow's data centers. Now, before I talk about tomorrow's data centers, what are today's data centers? Well, they're facilities hosting millions of servers. Here's a picture of a 250 megawatt data center in Bedford, Virginia, which is almost 1/5 of the way to Doc Brown's 1.21 gigawatts. Now, one of the reasons why data centers are getting so large is because of the end of this phenomenon that architects have called silicon scaling or Dennard scaling. And a nice way to explain that is, if I took a rack of servers from 2005 and I brought it forward to 2015, just the improvements of the circuits in those servers would have given me about 20x performance boost. But if I did the same thing and moved them forward to 2025, they'd only be about 4x better. And in order to match that 20x performance gain, I would need to buy 5x the amount of servers. So what today's data center providers are doing is actually starting to go towards vertical integration, where they build their own products to address this performance gap. And just to give you an example about what data center providers are doing today, 3 full custom solutions already deployed in production are Google's Tensor Processing Unit, which is a machine learning accelerator, Facebook's FBOSS switch hardware and software stack, and Microsoft's Catapult, which is kind of an FPGA that sits next to their CPUs and is able to parse network packets and do network acceleration. So the needs of the data center, this unique computing environment, is driving like internally developed solutions at all levels. But you may have noticed I left one out, which is the server socket itself. Now, what are the requirements for a server that's architected for the data center? In our lab, we think it's 3 things. It should be specialized for latency critical applications, because 100 milliseconds of latency gain has been shown to give you $400,000 annually at scale. It should accelerate common machine learning operations because of the commonality of machine learning in today's software, and it should be architected ground up for security. So our big research question is, what should a server under these requirements look like? Well, to talk about the latency critical requirements first, I just want to set some of the context about how fast today's data center networks actually are. Current NICs can push 200 gigabits of bandwidth and give or provide the server 220 million IOPS. And even more than that, the Ethernet Alliance has already published a roadmap, which you can see on this slide, of bandwidths up to 1 terabits per second. And the network protocols that are already deployed today, in addition, they provide microsecond scale round trip latencies around the data center. So at such bandwidths and latencies, how can servers really keep up? The performance onus is really on the endpoints now in order for them to actually keep up performance with the network protocols. So when we studied this problem, we started looking at the data center communication stacks. And to give you an example of what these communication stacks look like, consider that data center applications use a whole bunch of different programming languages and data formats, because languages and formats are, they're most adapted to different needs. You might have applications in Python and C, in Ruby and JS. And sending messages back and forth between those applications requires this process called data transformation. So consider application 1 sending a message to application 2, and that message is a person object that has an ID, which is an integer, a name, which is a string, and a phone number, which is itself a message. And in order to send that over the network, application 1 must first serialize the object, and application 2 has to deserialize it on the other end of the network. And when we measured this data transformation process, we realized it was an order of magnitude already behind NIC bandwidth. It only is about 1 to 2 gigabits. And today's NICs are easily 40 gigabits to 200. So how do we solve this problem? Well, by studying the software frameworks for data transformation, we realized the only thing really preventing these transformations from happening in parallel is actually explicitly communicating that parallelism. The data for the person object is already in memory, and we already know the layout of it when it's created. So all we need to do to reap that parallelism is to actually just communicate that layout with a better abstraction. So to that end, we designed something called a transformation schema, which contains the address for all the fields of the person object. And we designed a hardware accelerator we called Optimus Prime, because he's the data transformer, to do all this in parallel. And really by kind of designing this cross-layer solution, we achieve data transformation at the line rates of today's NICs. We also have many projects continuing in operating systems and networking and architecture. We're looking at how to accelerate other layers of RPC, of intra-service RPCs, like, for example, encryption and request scheduling. We're also looking at other bottlenecks in the memory hierarchy and the CPU pipeline. We recently had a paper in ISCA 2020, just this year, that shows that at such high bandwidths, you need to actually deliver packets directly into the L1 caches. Otherwise, the memory system, like DRAM, was just too slow to handle the incoming traffic. And we also have a project looking at, can we replace DRAM with flash, actually, to serve online requests? And what kind of hardware support is needed to get that, to get throughput using these systems? And because our lab works at the interface of OS and architecture and software, we think it's a good place to collaborate and contribute, and hopefully we actually get to see you at EPFL with you in the fall. The next thing I'd like to talk about is this is neural networks and how the demand for them is just exploding. So you may or may not know that Google's speech recognition assistant actually uses a deep neural network, and they came out in 2013 and said that if the average person using their data center for assistant used it 3 minutes per day, it would increase the load on their data center by 10x, which is just impossible, right? You'd have to buy a 10x bigger data center. So this problem is even getting bigger because neural networks are spreading throughout data center services. People now use them for ads and for translation and for natural language processing. And with the addition of all these frameworks like PyTorch and TensorFlow, it lets users run their own neural networks and train them. So without an accelerators, you'd need a massive data center, way bigger than 10x. So given that we know we're going to need accelerators for this, we started looking at how do you build one accelerator to rule them all, to use the expression. And the workflow to deploy a neural network, it really comprises 2 steps that the accelerator needs to support. It needs training and it needs inference. Training is when you actually build the neural network and feed it with its data set, and you figure out exactly what its parameters are and how it's going to classify its inputs. And that's an offline operation that needs a lot of throughput. And inference is latency critical, because when you request something, like with Google Assistant, you want your response as fast as possible. So if you look at that figure, that small figure on the right there, you can see a bunch of users requesting things, and all the DNNs have to finish the inference as fast as possible. And to that end, inference accelerators use reduced precision arithmetic. And that lets you squeeze bigger models onto your chip because there are less bits to store. And it lets you use integer arithmetic, which is faster and cheaper than floating point. However, prior wisdom actually says that we still need full precision floating point arithmetic for training. So when we're looking at what kind of accelerator for training and inference, we're looking to break that trade-off between training and inference arithmetic. And a cool solution that we came up with, which we published in NeurIPS 2018, was to look at how these numbers are represented in floating point for training. And you may or may not know that floating point numbers in digital representations have a mantissa, which is the bits of the number, like 1, 2, 3, 4, 5, and then the exponent, which says how big the number is, and that gives it its range. And our idea is to share the expensive part, which is the exponent, that's what makes these computations expensive, is to share that among all the values in a group or a tensor, which people in machine learning call it. And you can see on the slide there how I've kind of put the exponent like a shared thing from all those mantissas. And by doing this, we actually trained some state-of-the-art neural networks, and we showed that we can actually approach the accuracy of full precision training and get the speed and the density of reduced precision arithmetic. And we demonstrated this on real synthesized hardware. And again, I want to emphasize that it's that cross-layer thinking between the actual algorithmic approaches and the hardware that allowed us to get this training result with dense arithmetic. We have a whole bunch of students continuing to work on a bunch of machine learning problems, like how you can schedule requests for training and inference, like on the same accelerator. We're actually looking for analog devices and asking whether they can show better performance or have better density. And we're actually also looking at what software improvements are required and what systems need to be designed for supporting such massive scale neural networks for training and inference. So our group works on algorithms and hardware and systems. We have a lot of projects, and we'd love to work with you on that in the fall. And finally, I want to talk about security. As most of you, I'm sure, know, today's chips are really overshadowed by all of these speculative execution attacks where VMs can attack each other and users can attack the kernel. And it's so bad that Amazon went on record and said they have to disable all multi-threading for their micro VM clusters. And in fact, this is really bad for them in terms of monetization, because if you know, as they've gone on record to say, that they make $10 billion a quarter from AWS, and also you understand that by disabling multi-threading, they have 50% less CPUs to loan out to their users. This can cost them, potentially hundreds of millions of dollars, these security flaws. And the same actually applies to cloud FPGAs that can support multiple user circuits on them due to partial reconfiguration, but that's just been disabled actually because of the security implications. And really what I want to explain to you guys about this as a root cause and get this idea into your mind is that actually the reason why these attacks are possible is leaky abstractions. Executing either instructions or a hardware circuit, it leaves behind some recoverable state, which can be recovered and extracted by like any one of the methods and attacks that are out there, like cache timing attacks or like power timing attacks even. Our group, in fact, has uncovered a few new leaky abstractions where we've managed to attack cryptographic cores and FPGAs based on power consumption. We've also managed to trigger hardware Trojan horses just based on the circuit timings with ring oscillators and FPGAs. And we've also been able to leak information based on timing leaks in the CPU's instruction scheduling. And our goal in our lab is really, we want to architect from ground up a secure server architecture and ask, what should go into a server like that? What are the primitives that it should provide? What's the contract that should be provided between the hardware and the software? Some ongoing research that you can participate in and collaborate with us and join us to work on is how can you design new abstractions for secure execution compartments inside VMs that allow processes and VMs to share code if need be, but also provide good security guarantees. We're also looking at real-time verification of secure FPGA computation. So for example, you have a controller that sits on your chip that checks the computation is secure while it runs, and it cuts the hard line if it's not. And finally, we have some work looking at improving FPGA place and route algorithms. For example, using parallelism and using the FPGA itself to parallelize the circuit place and routing for a next FPGA circuit, which I think is a cool little conception there. So there's tons of opportunities to collaborate with us in operating systems and security and hardware. And I'll finish the technical part there. I'll put up some slides of the other students that helped make all this research possible. There's a couple pictures of us there on campus as well as on our lab ski trip. So thanks for your attention. And I really hope to see you at EPFL in the fall. Goodbye.